Okay, so now that we've looked at the different types of radiation, now the decay. Let's look at fission versus fusion. So fission is splitting of the nucleus. So that's like the alpha decay, that's splitting, but a really small split. But this is maybe a little bit bigger. And then fusion. So fusion is joining of two smallers to make a bigger one. Both are accompanied by a conversion of mass into energy. So one, it's too much mass, it goes bleh, and energy is released. The other one is smash and energy release. Okay, so fusion, I don't know if it's going to show you the fusion one, but here's fusion. Joining two smaller nuclei to form a nucleus. High temperatures are required. So yeah, it doesn't happen on Earth. It happens on the sun or many stars. It's the fusion of protons to form a helium nuclei. And remember, a proton is hydrogen. Okay? And this produces the sun. So you smash a hydrogen and a hydrogen, you smash them together, you get a helium. Appealing as the energy source, its availability of light isotopes and fusion products are generally not radioactive. That would be like a massive bonus. It'd be so cool if we could do it. But it's not presently used to generate energy because of the high energies needed to overcome the repulsion between the nuclei. Because remember, you've got like a dense positive and a dense positive. They're not going to want to fuse together really, really easy. And another thing is it requires temperatures of about 40 million Kelvin. That's really hot. Those temperatures have only been achieved by using a hydrogen bomb. And yeah, we're not going to do that. Okay, so now we're going to start talking about the artificial transmutation. We're looking at some naturals. Now we're looking at artificial. So transmutation, remember, that is when you're switching from one element to another by some decay method or emission. So transmutation is induced by striking the nucleus with another nucleus or a particle. This is used in the synthesis of radioisotopes, making new elements. And we do have a couple, I'll show you in class, we got a couple on the periodic tables. And so the production of uranium series or elements following uranium on the periodic table. So anything after uranium, that is all man-made. In 1994, 3 atoms of 111 were synthesized and decayed within milliseconds of each other. So within milliseconds, they decayed. They're now up to 118 in all our names. Let me just make sure. Yep, they are all named. So first, artificial transmutation. This was accomplished by Rutherford. He hit a nitrogen-14 with an alpha particle and converted the nucleus to an oxygen-17 plus a proton. So remember what we were talking about before. You got conservation. So he struck nitrogen with a helium. You had to add everything up, and you're left with like almost like a proton emission. And so you got oxygen 17, 8, and no, it's not stable because there are, I think it's missing a nucleon, so it's an isotope, and you got hydrogen. High speeds are necessary to overcome the repulsion. Like I said, if you got two positives, it's going to be hard, so you got to like whip it at it really fast. The higher the nuclear charge on either the projectile or the target, the faster the particle must be going. So it's got to go, like, got to be shot. Strong magnetic and electrical fields are used to accelerate these particles. All right, so one of the things we have is the cyclotron or the atom smasher. Calcium-48 ion is accelerated to a high velocity in a cyclotron and directed at an americium-243. One of the numerous americium-233 targets target atoms with a nucleus of a proton and the neutron surrounding an electron cloud. So there's a bunch of them, and they just target and they shoot, right? An accelerated calcium-48 and an americium-243 target atom just before they collide. So this is what we're looking at, just before they collide. The moment of the collision at an accelerated, the calcium hitting the americium target. The residue of the collision creates a new 115 element that begins to decay, decaying with the emission of an alpha particle into element 113. And you can see here is an alpha particle, here's another alpha particle. So it's starting to decay, right? The spontaneous fission decay eventually results in two separate atoms of the previously known elements. So looking at this, it shoots whap. And this is what happens, okay? So here's the periodic table. And what we're really looking at, and these are labeled now, so this is not an up-to-date one, but we're looking at anything after uranium, which is right here, so 93 up, 93 in all of those. All right, so then we got this place called the Fermilab. It covers 10 square miles, like this whole direction, with a all the way around, and a 4-mile diameter. Magnets in the ring accelerate ions to near the speed of light, then smash those atoms. Some atom smashers are built underground. And this is showing you a little bit of the Fermilab, which is so cool. All right, so neutrons are often used to induce artificial transmutation because there's no repulsive forces. Remember, neutron is neutral, it's Switzerland. So the absorption of a neutron destabilizes the nucleus, and it's used to produce cobalt-60, which is used in radiation therapy for good purposes and in nuclear plants. So this is called nuclear caption. So we've had beta decay, alpha decay, positron emission, electron capture. So now we're looking at neutron capture. So this is an example of neutron capture by uranium-235. You see uranium-235 captures, grabs onto a neutron, and conservation of energy, right? So whatever's on this side has to be on this side. So when this happens, it makes uranium split into two smaller particles and two neutrons. So it's like you shoot one in, you get two back. This will make sense when we start talking about reactors. And then it produces xenon or and strontium. So it makes strontium, xenon and strontium, and two neutrons. So how do we write this equation? Because it's kind of crazy. So let's look at polonium-209 when it captures a neutron and releases an alpha particle. So we already know 209 is at the top. We have 1 for the neutron and 4 for the alpha particle. So we have polonium, neutron, and an alpha particle. And we got to figure out what that's going to be. So next I'm going to do, we've got 84, you know that's a 0, you know that's a 2. So now we just got to figure out what this is. So whatever's on this side has to equal this side. So 210, 6, so this has got to be 106, and then we want an 82. So right there, see, 206 and 82. 82 is lead. Separating emanations. So how can the type of radioisotope be determined? The emissions of particular nucleus are passed through a charged field, and their deflection indicates the charge on the particle. So how the heck do we know? If there's a positive alpha particle, it'll go through and go stick to the negative. If it's an electron or a beta particle, it'll stick up here. Positrons will stick down here. So electric field deflects charged particles. So there's the lead block, it shoots out a particle, and it's going to do one of two things. You got positive this side, negative this side. So looking at C, C wants to go towards the negative, so it's got to be a positive particle, just like I was talking. It's repelled away from the positive plate because, yeah, it doesn't want to be there. So it could be an alpha particle, a proton, or positron. So 3 different things. Well, let's look at the A. A goes towards the positive, so it's got to be a negative, which means a beta, or possibly an electron. It doesn't say electron here, but I would say electron. So path A is created by a negative particle attracted to the positive plate, repelled away from the negative plate. So there's the beta. Well, what about B? What's B? It goes straight through. It's got to be a neutron or gamma radiation because neither of them have a charge. They're not attracted nor repelled by either side. Energy changes. So total mass of the products in a nuclear reaction is slightly less than the mass of the starting materials. Nuclear reactions do not show conservation of mass. Small amount of mass is converted into energy. Oh no. So the energies involved in nuclear reactions are calculated using Einstein's famous equation, E equals mc squared. The proportionality constant is C2 is so large, even small changes in mass cause large changes in energy. The amount of energy released through the fission of 4.5 grams of uranium-235 is the equivalent of burning 15 tons of coal, which you can kind of see why this might be a good idea to use as an energy source. So what I'd like you to do is finish up working on the nuclear charges 2. And if you have any questions, make sure to ask. I hope you guys have a great day.